enjoyed the silence for the moment. And okay, we heard already kind of a little bit of this nice Anscombe example, and I'm kind of trying to do a little bit similar things. I'm interested also in visualizing kind of not now the tree space, but how we can compare different rate across site models. And I'm not sure if you have been to the first part of the sections. Jay actually introduced kind of almost everything I wanted to show now. I'm just kind of talking mostly about discrete gamma models and a little bit of invariant site models and a little bit more of discrete gamma and invariant site models. And all these kind of models were of course introduced from Xiang Yang and Peter Bodell kind of a long time ago, and they seem to kind of have taken over when you do phylogenetic reconstruction. They're kind of probably so popular because they have few parameters, they're pretty easy to compute, they seem to work in most of the times, but there is a little few problems. The rate across site models, we're usually not really interested in them, so we are actually interested in the topology and maybe the edge lengths, but the rate across site models, they're really used as hyperparameters. There's maybe some of these site models are a little bit an exception, and that is if you look at codon models and look in which sites are under positive or negative selections, but if you estimate a GTR plus gamma plus I model, you're usually not really interested in the kind of parameters of the gamma plus I. The other problem is it's often reported that the shape parameters and the invariant site parameters are correlated, and there's also some studies where we see that the edge lengths can also be correlated, and of course edge lengths and rates kind of are confounded, so it's kind of we kind of have three parameters, and they all can kind of cause a little bit confusion. And I hope I can highlight a little bit how we maybe better present these parameters. And the motivation was kind of just recently, Richard Neha kind of put out on Twitter that he had a kind of nice data set with HRE sequences, and he fit kind of different number of rate classes to it. And so when he had kind of these classical 4 rate parameters, the edge length was 3 times as high, the total edge length of the tree, than when he had more rate classes. So he asked, am I doing something stupid? And we'll hopefully see that he actually didn't do any stupid things, but we probably should be a little bit more careful when we estimate these models. So this kind of phenomenon was already kind of observed by this paper from here, the first paper, so I don't want to mess up the names. And there's also just last year was a nice paper from Nugent, Arndt van Herslaan and Min. I think they're probably in the audience, at least one of them. And they've kind of estimated kind of over different parameter space and found a lot of kind of local optima in the trees. And kind of they were interested in kind of which one of these local optima is really the global optima. I kind of want to look a little bit in how different are actually these local optima. And so if we speak about the gamma distribution, we usually kind of see these kind of gamma distributions, and I plotted kind of quite a few different ones. So if we have these kind of, the classical one is kind of the shape parameter is larger than 1, then we kind of have these Gaussian belt curve like, and if they're kind of, if we have a shape parameter of 1, then it's kind of this exponential distribution, and if we have a shape parameter which is pretty low, then kind of all the mass is actually going towards 0, and kind of I not only plotted the density, but I also plotted the cumulative distribution function, because when we look into the discrete discretized versions, this seems to make more sense to compare different trees or different shapes better. And so how to construct gamma distribution. So I'll do it again, even it was kind of in one of the talks beforehand already. So we have kind of our gamma distribution, and the usual approach is we kind of cut this distribution in equals quantiles. So it's usually 25% if we have k equals 4 and we don't mess up with the default values of our program. And so now we have, then we kind of compute for each of these quantiles. We kind of compute for each of these areas either the mean or the median. And this kind of I did here. And here we kind of maybe see already a little bit. So the mean and the median for this specific case look very similar. But the thing is, if we have kind of the density is now just these kind of sticks, and they're not really good to kind of compare different distributions. But if we have a cumulative distribution function on the right, we actually can see nicer where these different distributions differ. And now I did just this kind of, here we see with the, if we have a really low shape parameter, kind of all the kind of the first three rate classes are really bumped together. And the other kind of observation is that the fourth shape parameter is close to 4. And this is something which is kind of a little bit oddity, which we can figure out soonish. And I just kind of have these different shape parameters, so now they're a little bit better behaved. So usually we have kind of this nice condition that our distribution, or if we have a density, it should sum up to 1. And so if we have kind of these p is kind of 1 divided by 4, then we have kind of this constraint that we get 1 and we kind of get a maximum rate of 4 if we divide it by 1/4, and then it's 1 and all the other rates needs to be 0. And that is kind of a little bit a problem. And so here I actually showed what is kind of the maximum, or how does the, when we vary the shape parameter, what is kind of the mean of, or the median of the highest rate class. So you see kind of here these kind of, if we integrate or take the, kind of take the mean or the median of this kind of gray area and kind of vary the shape parameter. And if we get with the shape parameter close to 0, we kind of get for the mean towards 4. If we actually get, take the median, it actually goes down, which seems to be very unintuitive. But the thing is, now I navigate back. And if you look at the cumulative distribution function, if we go closer to 0, then actually here this area grows and we kind of get all most of the weight towards 0. And if we take kind of the median of this class, we get kind of over these 87.5%, and we actually dive into 0. So it's a kind of really weird oddity of these models if we have these equal sized rate classes. And yeah, so in a sense if we have these kind of equal sized rate classes, we have kind of these kind of two extreme cases. If we have a shape of 0, we kind of have invariant site models where the proportion of invariant site is 75%, and if we have a shape of infinity, we kind of have the same as a one-rate model. So that's kind of kind of the really kind of two extremes. And now if we have a discrete gamma plus I model, we kind of need to reform. We have one parameter more, and we need to update our rate classes and weights a little bit. And it's kind of just here we have kind of one of these nicer normal gamma distributions, and then we kind of have a little bit of an invariant side parameter. So if we have kind of here 0.1, and then when we have the density or the distribution functions, we just jump at 0 up. And so you can see kind of the distribution, the density is getting a little bit lower, and we kind of, the weight goes a little bit, the rates are actually getting bigger, the maximum rates. So now let's look at this example from this HIV data set again, and we see when we kind of plot, I kind of redone the analysis also in the Schliep program, but it's probably exactly the same or very similar to all the other programs. So we plot here the cumulative distribution function. We actually see one of the problems. If we have only 4 rate parameters, our maximum rate is limited to 4. And if we have, and that's kind of, if we multiply, our rate should be something like 10, we kind of compensate with the edge lengths to make a nice distribution. And this is kind of, I think, the main point I want to make. Here we kind of plotted the parsimony scores for each of the sides. And the parsimony scores kind of are a nice lower bound for the expected number of substitutions each side should have. And then we kind of can do our gamma models to kind of compare them, and we see we can't really, since the edge lengths and the rates are confounded, they don't really make much sense of themselves, but actually the 4 rate model doesn't fit necessarily badly. The 20K model, this is 20 state rate classes, fits kind of better. You can also see that there's areas where probably the gamma distribution is not really good, like here in this area. We also have to think about that the p-score is actually an underestimate, so it's probably we should be on the other side a little bit. But it's kind of, I think we can kind of compare where are problems and when do things fit or not fit. And so now I also have a few examples from the other paper where they had the multiple optima, and I'm not sure if you can read it, but the darker, the one line has kind of a shape parameter of 0.5 and an invariant side of 0.2, and the other one has a shape parameter of 0.68 and 0.3, and the distributions are almost identical. So I think if you do some simulation on these two distributions, it will be hard to distinguish them. So it's kind of maybe are these kind of different optimizations. You get very different values, but the distributions could be, in the end, look very, very similar. Yeah, and this is kind of with different kind of parameter sets, and again, the distributions are actually, when we look at the cumulative distribution functions, they look very, very similar. Yeah, and you can construct, if you want, some multiple optima, when you kind of just use kind of an invariant side model and or then to these other extreme and kind of go with the shape either towards 0 or to infinity, so you kind of get exactly the same distribution. So that's more a try example. And yeah, that's pretty much is it. So I have to thank kind of to all my lab members or the lab members of the Rebel Lab. And yeah, I'm founded by NSF, and UMass Boston gave me also some money, and Elizabeth Armand and Cécile Arnay and John Rhodes kind of bombarded me with lots of other useful information. Thanks a lot.